Hi, good morning. Today we're going to look at the first topic of our physics 150. Alright, so refer to your PHY 150 summary I just sent this morning. So there are altogether 8 topics. Okay, 8 topics, and the first one we have is Coulomb's law. But before we introduce to Coulomb's law, right, we need to look at the charge. Right? Charge. What are charge actually? For example, electron is a negative charged particles, proton is a positively charged particles, and there's only 2 types that you know. Another type, of course, is a neutral particle, for example, like neutron. Right? So these are the 3 examples of charged particle and neutral particle. Now, what is actually charge? Charge is the intrinsic property of particles that we cannot change them. Okay, is the charge of electron and the charge of proton really the fundamental value with a certain amount? For example, electron is 1.602 times 10 to the power negative 9 Coulomb, and the same goes for protons. Okay, but recent study under quantum mechanics, we realized that the charge for electrons and the proton is not really that fundamental. There are some things that is even more fundamental than the proton itself. Well, we leave electron alone. Electron is a very funny particle, right? Now, for the proton, it actually consists of 3 other particles which is even smaller, which we call quarks. And that one, to study them, you need to take up physics in degree, okay? And then you have to take quantum mechanics and then particle physics. Alright, so we don't go into detail for that. So ours here is very simple. There's only 2 types of charge. We have positive charge, okay, and then we have negative charge. Right, so 2 types. The neutral one we don't want to talk about. And then for the positive charge, the example will be proton, okay, and then the example for negative charge will be our electrons. Alright, so these are the very easy example, okay, for the particle, protons and electrons. So what we're going to study under Coulomb's law is what will be the interaction when we put them together nearby and even far apart. Alright, so there will be 2 types of interaction. So the interaction part, okay, the interaction. So when we put 2 positive charge together nearby, okay, 2 positive charge and also 2 negative charge nearby, what happened to them is they're going to repel each other. Okay? They're going to repel each other away, okay, like this. And the same thing happened to electron. So we call this one the same type of charge that repel, or like charges repel. Okay, like charges repel. The charge of the same type, okay, they repel. So we have to label them because they are forces and they are vector. Very important for you guys this semester. So in this case, this one will be F, F, and F. But since this one pointing to the left, we normally assign a negative sign. They will have the same magnitude but in the opposite direction. Alright. And the next thing is, what happens when we put 2 opposite charge nearby? For example, a positive charge and a negative charge nearby. Well, the opposite now will happen. Positive charge and negative charge, they attract each other. Okay, they attract each other. So we will call this one the F, and this one is the negative F. Okay, so we end up like this. Unlike charges attract Okay, unlike charges attract, unlike means they are not the same. Okay, they are one positive, one negative, so they will be attracting each other. It doesn't matter what are the sources of the charge. It can be a positive ion, it can be a negative ion, or it can be a proton, it can be an electron like a hydrogen atom. Alright, so this is the interaction between them. So now someone studied this phenomena and it's called Coulomb's, and it actually summarizes in one very simple law. We call that one the Coulomb's law. Okay, Coulomb's law. Now let's assume, okay, this is number 3. We call it Coulomb's law. Okay, Coulomb's law. So under Coulomb's law, you have statement. What did he say before we look at the equation? So this is Coulomb's law. Coulomb's law states that if you have a, let's assume a positive charge here, which we call Q1, and then at the distance away, another charge, let's say positive also, which is Q2 at the distance R. Alright? So these two charges, they will repel, of course, with a certain amount of force. They follow this straight line. Okay? They follow this straight line, and the force is F, and this one is F. But now, we are not going to use positive and negative. We are going to use subscript, because we have the subscript for the charge number 1, which is Q1, and then charge number 2, which is Q2. And this force, we will label it as F12, and this is F21. Now, F12 means the force acting on charge number 1 by charge number 2. And the vice versa also happen like this. For F21, it means that the force acting on charge number 2 by charge number 1. Alright? So the distance between them is R. So now, quantitatively, we want to look at what Coulomb's have to say for this condition. So Coulomb's law states that the electrostatic force between two charges Q1 and Q2 is directly proportional to the product of their charges Q1, Q2, and inversely proportional to the square of the distance between them, which is R squared, like that. So number 1, it is directly proportional to the product of their charges. That means Q1 multiply Q2, and then the second one is inversely proportional to the square of the distance between them, 1 over R squared. So if we combine them, we get something like this: Q1, Q2 over R squared. That is the proportionality. Alright? So we're going to change it into equation, okay, so that we can get the Coulomb's law equation. So if we change it into equation, we have this: F is equal to K Q1 Q2 over R squared. So now we have a full equation and with a constant K. Okay, with a constant K. So we will call this one equation number 1, where your K is called Coulomb's constant. Okay, Coulomb's constant, and it has a value of this: 8.99 times 10 to the power 9 Newton meter square per Coulomb square. That is a value discovered by experiment, okay, from Coulomb's experiment. So the K value is called Coulomb's constant. Okay, so by using this equation, we can calculate For example, the force between two charged particles when they are placed at a certain distance. Okay, for example, look at one example by using this equation. So we look at example 1. Okay, let's say there are two charged particles, Q1 which is 10 microcoulomb, and then at the distance r which is 1.2 meter, another positive charge which is Q2 equal to 7 microcoulomb. Right? So we calculate the force between them. So the force between them, let's say we have two forces here. This is F12, this one is F21. And since we are only interested in the magnitude at the moment, okay, we calculate the force 21, let's say, okay, force 21. So the force 21, the magnitude is given by the same formula here, okay, Q2 Q1 over R squared. Well, why I put Q2 Q1 instead of Q1 Q2? Well, they are the same answer, but because we want to follow them so that you don't put in the wrong charges, F21 you have Q2 Q1. If I calculate F12, you're going to have F12 here, and this one is Q1 Q2, but it doesn't matter, they will be the same. Okay, the value will be the same in this case. So we put in the value and calculate the magnitude of the force F21. That will be 8.99 10 to the power 9, and then multiply by charge number 1 10 microcoulomb, and then number 2 is 7 microcoulomb, divide by distance 1.2 squared, and don't forget the magnitude. Alright, a moment when I calculate the value for these forces. Okay, so the answer is 0.437 Newton. And 0.437 Newton. Well, that is one way in using Coulomb's law in calculating the Coulomb's force or electrostatic force. Okay, forgot to mention, electrostatic force is a force that existed between two electrically charged particles. Okay, so that's an example. But now let's say, what happens if we put that two charges in a different environment? So far what we are assuming here is the charge will be in like normal lab condition, which is in air or in vacuum, because air and vacuum have quite a same electrostatic property. So if we put them in liquid, let's say in water, will it still have the same value of this 0.437? Well, from experiment, you will discover that, okay, if the charges Q1, Q2 are in water, the force of the magnitude of the force F21 is no more equal to 0.437 Newton. And that seems to be a problem. It is not the same. It is actually very, very much smaller. The actual value will be roughly 0.00. Okay, the actual value 21 in water is roughly equal to 0.00546 Newton. This is about 80 times. It divided by 80 times. Well, there is a problem facing by Coulomb's initially. So that means what? It means your formula is not a general formula, because you can only calculate the force between two charged particles or any two particles when they are in air or in vacuum. When you put them in some other liquid, they change. The forces change. So why they changes? Why you cannot use this formula? That means it's not general. This formula is only good when you have the two charges in air or in vacuum. So they go and find out, they go and do experiment to find out what actually is the value of K. So then they realize from experiment, so in general, the K is not that value. That is a special case. It is the K value for vacuum or A. Okay. In general, that means in any medium, the K value is given by this 4 pi epsilon naught epsilon r. That is the complete equation for the K value. Alright. So now, what is epsilon naught? Epsilon naught is a value that is given like 8.85 10 to the power minus 12. This one is farad per meter. And then it is called the permittivity of vacuum. Or normally books say free space. Okay, we don't want to use free space because free space and vacuum there be a little bit of different there. Now the next one is the epsilon r. This guy here is called the relative permittivity. Okay, the word permittivity, it seems like how much percentage of energies electromagnetic field is allowed to pass through. Now when we talk about why here electromagnetic field, because charge number 1 and charge number 2, how do they interact? They interact through electric field. Okay, electric field. So electric field pass through a medium. When the medium are different, they will lose a certain amount of energy. That's why when they put them in water, their value will be different. Because water, when electric field pass through water, they need to excite the water molecule, and then from one to the next, one to the next. So they will slow down, number 1. Number 2 is they will lose a certain amount of energy. That's why by the time they reach there, the effect of the force between each other will be very much reduced. So that means for water, when you put 2 charges into a water, the force between them will be reduced by 80 times. Okay, so because of that, salt can easily dissolve in water much better than oil. Alright. Okay, this relative permittivity is referring to the medium that you put the charge in. Okay, so this value for water is 80, and then for vacuum or air is about 1. So look at some of the example. These are the example of medium and their epsilon r value. So vacuum will be defined to be 1.00, and then air will be roughly 1.003 like that. And then for water, which is very common to us, these two things, this one is about 80. So that's the reason why when you put that 2 charges, you recalculate the force is 80 times less than this one. Alright. So that is now it's going to become a general formula when we put this one in here. But if question didn't say anything about a medium, you have to assume it is vacuum or air. So that means you're going to use epsilon r equal to 1, and when you put in here, your epsilon r equal to 1, your k equal to 1 over 4 pi epsilon naught only. And when you calculate this, it goes back to this value. Let's show it here. Okay. So now we write off this one and we recalculate the value of the k. Okay, so we call this one now example number 2. So calculate the value of k in vacuum. Okay, calculate the value of k in vacuum. So we have that k formula is equal to 1 over 4 pi epsilon naught epsilon r. Now, because in vacuum, our epsilon r is equal to 1.00. So now I put in this value. Your k is equal to 1 over 4 pi multiplied by epsilon naught here, 8.85 10 to the power minus 12, and then multiply by 1. So if you use calculator, you get that value 4 times pi times 8.85 10 to the power negative 12, and we get this 8.99 10 to the power 9. Okay, 10 to the power 9. Newton meter square per Coulomb square. Okay, per Coulomb square. So that is the value that you use under special condition. In our case, it will be normal condition. We have this value that we use. So that means the equation finally will end up like this. From number 1, our formula generally become this: 1 over 4 pi epsilon naught epsilon r q1 q2 over r square. Alright, that is number 2. So this one is a general case. This one will be special case, where your epsilon r is equal to 1. Alright, so that is all for our Coulomb's law for this session. For the next video, I will show you how are we going to use the Coulomb's law formula, this one or this one, in a more complicated example. Alright, thank you for watching.